All right, before I get to answers to the equilibrium review and the additional practice, I'd shown this to one of the tables today, and I thought it would be beneficial for others to see. If I were to be given a chemical reaction, and I don't know particularly off case if this one is endothermic or exothermic, so I'm just going to make that up at this point. But let's say that this was a positive 90 kilojoule per mole of reaction was the enthalpy of this reaction, meaning I know that the forward direction is endothermic. What that means is that I can think of heat as being its own reactant. This reaction, the forward reaction, requires heat. Heat needs to be put into these reactants in order to form products. And therefore, when I start changing temperature, I can say if I increase temperature, that would be similar to adding heat. So what the system is going to do is it's going to respond by shifting to remove the heat. All right, and that would be the side that doesn't have it. If the reaction were to go to this direction, that means it would be generating more heat. But if the reaction is going in this direction, that means it's using up the heat. And so that's how I would know that this reaction would shift to the right. And again, whenever I say shift to the right, that means when this establishes equilibrium, and it's going to be a new position and a new equilibrium constant, there will now be more products in that system than there were prior to the temperature change. Right? So that's another way to think about it, where if I say, hey, if I decrease the temperature or remove heat, then that means I want to shift to replace it. Right? So if I want to shift to replace it, that means I want to be going to the side that's generating the heat, that's producing the heat. And so that's going to be the reverse reaction. That's why we would say this one's going to shift to the left, that once it establishes a new equilibrium, then it's going to have more reactants in that container, in that system at equilibrium. So I just don't know how well a College Board may or may not accept this. Again, if we understand Le Chatelier being a countering of the stress that was caused. So the idea being here is the stress, and then here's the system's response to that stress. The stress was the addition or the removal of heat. The response is to shift to counter that. Very similar to what we talked about with pressure, right? That if your stress caused an increase or decrease in the number of collisions, the response was to shift to counter that change in collisions. All right, so with that, I'm actually going to go through a number of different things. I was going to also put up the answers to these equilibrium questions that I had done selected problems in class. So I'm going to scroll through these pretty quick, and as per usual, pause as needed. So here we have number 1 and then number 2 letters A through C. Here we have D through G. And then I got to zoom in on every page. Here we have H through K of number 2 still. And then number 3, A through E. Then we have number 4 and 5. There's number 6, A and B. B would not be relevant to your exam. Here's A of number 7. Looks like there's the rest of number 7. And then here's B. Number 8A. 8B. 8C. Another KPKC conversion. 9A. 9B. 9C, not tested. 10A. 10B. 10C not tested. 11A. 11B. 11C, which wasn't sketched on the graph, but we did that one in class. Oh, here they are. There's the line for 11C, but we did that in class. And D. 12A and B. C would not be tested. 13A and 13B. And C. All right, so now we get to the equilibrium review. So here we have question number 1. Please notice the assumption that was made and what portion of the calculation was crossed out. I also find a lot of students didn't write out this expression, and so they forgot to include the squared terms in their numerator and denominator. But the final answers are down here. I just added an F for final. That's the answers after evaluating X. And then here's 3 and 4. There's 5, and here's 6. On the back 7, again, assumption made. I've shown you what I've crossed out. Final answers are underneath the rice table. Number 8. Number 9 required the use of Q to determine that the reaction needed to proceed in the forward direction to get to equilibrium. It also was a perfect square question, so a number of students were having difficulty getting from here to that value. That is something you need to practice. It is the hardest thing that could be asked of you math-wise, in my opinion. So I think that makes the possibility of it not as great, but that doesn't mean that it's not a possibility. And lastly, number 10. These are all of the things that you could do. All right, and then let's take a look at those additional problems from the textbook. I just snagged the answer keys from the textbook. So here was the first problem, number 37, A, B, and C. So all of the work with answers. This one involved using the ideal gas law to determine the partial pressure of each gas. Then here was 45, where it involved using the ideal gas law to convert a molarity into a concentration. Really, this is what I would have taken away from the ideal gas law. They showed a temperature conversion, but yeah. All right, so here we go. They did not show a rice table for this, but if I were to do a rice table, it would have looked like this, and I would have X'd these out. So I would have started with initial concentrations of my ions is 0, and then that means I would have been producing X numbers. So this is what they did instead. They just said at equilibrium they would equal X instead of showing the entire rice table. And so they solved for that concentration. But then a saturated solution of this would be that concentration, because everything is a 1-to-1-to-1 ratio here, right? So technically it's never in that format of the combined calcium sulfate crystal. When it's saturated, it's dissolved. But we can still say that its concentration would be the same for the amount of the compound that then dissociated into ions. So at that point, it just becomes a series of molarity and mole conversion calculations. This right here is molarity times liter. That gives you moles if you were to stop there. And then here, this is molar mass to convert from moles to grams. But remember that mole is equal to molarity times liters. Okay. All right, this next one here, the last one, it involved just more solution types of calculations because they started with grams. So first thing I had to do is this is gram and then this is molar mass. So this was my converting grams to moles in this portion right here. But then once I had moles, I divide moles by liters to get molarity. So we have a combination of going grams to moles and then dividing the moles by liters to get the molarity of the diatomic bromine. And then once I had the molarity of the diatomic bromine, it just took solving this expression for the atomic bromine, not the diatomic, the singular bromine atom. So that's what this equation is, solved for the single bromine atom, and then coming up with that molarity. And then now we're going backwards. Now we're doing molarity times liters to get moles, and then we're using molar mass to get grams. So very similar to what we did in this question right here in terms of combining solutions and molar mass, grams, moles, all of that stuff. All right, if you have any additional questions, please let me know.